So this session will run a little bit late. Apologies for that. We're 15 minutes late in starting. Mostly my fault, I suspect, but anyway. So first thing, just some administration before we start. First one, if you're going to the social event tonight, please pick up your tickets from the registration counter. If you don't have a ticket, you will not be able to go. So please collect a ticket, first come, first served basis. The second announcement, this one is really important. For the wireless network, please use the wireless called APRICOT. Right. Please use the wireless called APRICOT. That's running on 802.11a. We have lots and lots of channels of 802.11a for you. Please do not use APRICOT B unless you have no choice. We had problems during the opening plenary. Everybody decided to use APRICOT B and it got completely swamped, which is why it wasn't working. We expect everybody to use the APRICOT SSID. The passwords are the same. Please use APRICOT A. 802.11a is way better than B for this type of size of event. Third thing, we also have a V6 only APRICOT SSID. If you want to live in the V6 only world, you can go and play with that. We also have a 464 XLAT, one of the V4, V6 transition techniques. We've got an SSID of that, and that's all working, kindly provided by our friends from the Japanese internet community, so we appreciate their support in putting that up. So please try it out. There'll be a talk about that later on in the week as well. So if you try it out, they can gather some data and they can present the data later on in the week about what's going on. So I think that's probably what I need to cover by way of introduction. Now, this is APOPS we use for the APRICOT plenaries, so the technical plenaries. APOPS is the network operations group for the Asia-Pacific Internet, as I've put on the screen there. It's chaired by myself, Tomoya Yoshida, and Matsuzaki Yoshinobu. So the three of us steer this as we can. I don't see Tomo, but Maz is sitting down there in the corner. He will be chairing the session that takes place tomorrow morning. There is a website and there is a mailing list. Both are pretty quiet. So it's part of the APRICOT program. It's also part of the mid-year APNIC conference. It's the technical and operational plenary there. We do a general call for contributions, of course. Most of you will have seen the call for papers going out several months ago and frequent reminders after that. Program committee is formed from the community as well. The program committee, several of them are here at the conference. They've been working pretty hard, especially in December and January, to assemble the program for the whole conference, not just for APOPS itself. Just a reminder, you'll get an email about this if you haven't already got it. Call for the lightning talks. Lightning talks are 10-minute presentations, no slides needed, taking place on Thursday, 9 a.m. to 10:30. If you've got a bright idea, want to talk about it for a few minutes, it's an informal session. Dean Pemberton is going to be chairing it, so please, if you're interested in talking about something, please submit it. Papers.apricot.net, select lightning talks, otherwise we will not see it. We already have had 3 submissions. We've probably got room for, I don't know, 7, maybe 8. So make it interesting and you may get a chance to talk about your topic to the community. So today's agenda is this. So I've done the introduction. We're going to have 3 presentations. First one up, from Olaf Kolkman from NLnetLabs, Innovation at the Waste. Then we're going to have Dave Meyer from Brocade talking about past, present, and future trends in networking. And then finally we have Kobi Hasharoni, who's going to be talking about high-end routing platform using a chip-to-chip optical interconnect, which also I think you will find very interesting. So enough of me talking. I think I'll now invite Olaf to come and be the first speaker. Welcome.
Thank you, Philip. The innovation at the waist. This slide says music. These are a few thoughts that I had over the last year. And it's not going to be a deeply profound technical talk. There's hardly any technology in it. It's more marketing. And now this should work. Let me see. Yeah. So who am I? My name is Olaf Kolkman. I work for NLnetLabs. I'm director of that group. We do open source and open standards development. We're active in the ITF. We write a bunch of name server software, and we've been evangeneering IPv6 and DNSSEC. The reason why we do that is because we believe that the internet, an open internet, should be open, global, trustworthy, and should allow for innovation. That's something those are core properties that make the internet a valuable system, a globally valuable system. And when we think about IPv6 and DNSSEC in that context, then we've seen that that type of technology, IPv6 and DNSSEC in particular, have a difficult time being deployed. And that makes you back the question, is it actually possible to innovate at the waist of the hourglass? If you don't know what that means, we'll get to that. But if you talk about innovation, what is innovation and what drives innovation? Now, if you then Google for innovation, you very quickly arrive at work of a guy called Everett Rogers, who in the 60s did marketing research, in essence. And probably you all seen one of the sort of seminal graphs that came out of a study called Diffusion of Innovation, which is the deployment S-curve. You probably all heard about innovators, early adapters, early majority, late majority, and laggards if it comes to adapting technology or if it comes to buying products. So Everett looked at what goes into these equations, what makes people decide on taking up innovation. So that deployment curve is about the take-up of innovation. And Everett looks at the decision stages that all individuals go through when they are at a particular stage. And so at each point of that innovation curve, you have a set of individuals that are at different decision stages. What are those decision stages? I'm going to describe them shortly: knowledge, persuasion, decisions, implementation, and confirmation. Knowledge. So knowledge is an individual that is exposed to an innovation but doesn't really know much about it. This is where advertisement comes into play in marketing. For us, for engineers, it is, you know, you might have seen an IPv6 configuration kernel option, or you might have seen some activity during an IPv6 task force meeting, or you might have heard about IPv6 in some sort of conference. I hope that within this circle, everybody has heard about IPv6, but I'm sure that my mother hasn't. So she's not even at this knowledge stage. Once people know about an innovation or a new thing, they will start to look around and try to get more information about it. They will try to persuade themselves whether that innovation brings something to them that is worthwhile. So what they will do, or what we do as technicians, internet technology persons, we'll talk to our colleagues, we'll read an IPv6 Wikipedia article, take a course, read RFCs, talk to our vendors, that kind of things. Or talk to your colleagues, you know, what is your experience with deployment of this material? An individual that makes decisions about, that is implementing an innovation or makes choices about that innovation, then makes the decisions. individuals weighs the risks and the benefits and takes the decision to adapt or reject. I'm going to go into what type of decisions are made, what goes into that in a bit. So it might be that at that moment, for instance, an engineer says to himself, this is a good thing to push. This is a good technology. I'm confident that this will work for us. Then they have to persuade the management. It's good to know that at that stage, your manager is at that first stage, is at the knowledge stage. Probably you are the first person to introduce them to that particular innovation or that knowledge. It's also important that once you said no to this innovation, you will have to go back to persuasion. Somebody else probably has to do that because you lost the active drive to be persuaded. So you're not seeking information, but new information needs to come to you in order to reopen that decision process. Okay, after you made the decision, you go to the implementation phase. This is where you have to do the real work. In this case, in this stage, you will also be looking for a lot of information about how to use the innovation. It might, you know, this applies to IPv6 as well as to detergents that you put in your washing machine. Remember that those liquid detergents were being introduced. Well, at the point that you decided on the implementation, you actually had to read the manual to see how much detergent went into these little balls that went into a washing machine, because that was something different. Anyway, this is another stage that is very common. Then there's the decisions, the confirmation stage. And this is the place where the pilot gets moved into production. This is where you actually confirm that your decision to go for implementation was a wise one. Huh? So, based on this, there are new questions to ask. How does knowledge spread? How can we effectively make other people aware about a new innovation? And how are those decisions actually made? Well, social networks. Social networks drive the spread of knowledge. People talking to each other. That's basically it. And that is most effective when there is a set of shared values, but a lack of awareness. Half a word is sufficient to, you know, sort of make other people aware of what you're talking about. Engineers that talk to other engineers and said, oh, we need more bits. Or it's a simpler message than talking to your management, where the shared values might be less. And it's even a more distant way to, say, speak to politicians or other types of social networks. If it comes to decisions, there are several decision types that come into this equation. There's the optional innovation decisions, a decision made by individuals, if you distinguish from others in the social system. I think that in the internet, that is the type of decision that is often made. You're loosely independent from others that make the decision, for instance, to deploy IPv6. It's your decision to do that. It's also not a collective innovation decision, because you don't say to each other, let's all do this. No, it's your own thing. And it's certainly not somebody who says the globe should deploy IPv6. There's nobody who has that power to say the internet needs to go that way. What are now, if you are an individual that needs to make a decision, what are the things that go in, what are the things that inform that decision? Relative advantage, complexity, simplicity, compatibility, triability, and observability are the things that go into that equation. Complexity, simplicity means, is that innovation difficult to use? If it's difficult to use, a person that needs to make the decision is less likely to adopt it. If it brings you know, a lot of complexity, you might think twice because it might break your network. Relative advantage. Does your innovation bring a relative improvement? Are you better off tomorrow than you were today? If that is unambiguously can be answered with yes, then the chances of adapting that innovation is high. Compatibility. Is the innovation relatively close to your knowledge, to what you already do? And this is very generic. Again, this also applies to buying television sets, or instead of a cassette player, move to MP3 players. Is it tryable? Can the individual try the innovation? Is it testable? Can you actually do this in a relatively easy way? And is it observable? Does it bring some coolness factor, or can you talk about the innovation at the bar? That's how I paraphrase that. So relative advantage, that has a link to value. As you know, the value of a network, is Metcalfe's law, scales with the number of attached nodes to that network as n log n. That's something I get back in. So now let's look at how this innovation aspects, how those things apply to the internet at large. I'm going to look at this using the hourglass model, where you have application layer at the top, you have network layer at the bottom, the network delivers IP, the application layer uses IP, and we're talking about, the thing in the middle. IP, DNS, routing, that whole thing. Interdomain. Well, I think that innovation at the application layer has been the ease of innovation and the ease of adaptation of new application has been sort of the cornerstone of the value of the internet. It is incredibly easy to bring new products and new ideas to the internet. And that's because you only have to talk IP, you don't have to put intelligence in the core of the network, or it used to be the case that you didn't have to put intelligence in the core of the network. No, it's basically connect and play. Colleagues at ISOC have called this permissionless innovation, and I think that is a very good term for a property that made the internet grow. So I think these are sort of the aspects that made that happen. New applications are deployed almost daily. They're proprietary, open source. There's no imposed business model. Things can be freeware, payware, adware, privacyware. Things just happen. I think it's a beauty. Imagination is the limit. We didn't think of Facebook 10 years ago. We didn't think of iPhones and stuff more than 10 years ago. And they all work because they run on IP and they could just be made. And for all these things, I think you can claim that they have a relative, for each individual adapter of the technology, they have relative advantage. Complexity, simplicity trade-off is easy. Compatibility with their lives is easy. It's tryable, it's observable. You download an application, you try it. If you like it, you throw away. You download a new browser, you try it. If you don't like it, you throw it away. On the network layer, picture is a little bit different. As you know, I don't have to explain this. Network of networks. And at each network in that complex system of the internet, individuals make within those ASs, make their innovation trade-offs. The good thing about IP is that IP became a commodity. It's a highly competitive market, and the prices go down, basically every day. This is a list of prices in Western Europe, early mid-2011. And The only thing that is expected from you as an ISP is that you deliver IP to the edge and route with your upstreams and your peers. It's the only thing that's expected. And how you do that inside of your network, that's your business. And innovating that fabric is an internal decision, where things like compatibility, observability, and triability are important, and some people will, take one technology over another and find that they have a better way and a cheaper way to push packets over their networks. And that brings in an early deployment advantage. You've just pushed down the OPEX of delivering packets while the commodity price is still high. That means you just make more money on delivering that single packet. While the persons that innovate at the later stages in the same equipment, they have seen the drop in the commodity price because everybody has deployed this new technology, so the price of the commodity drops, and because they're late, they are paying the additional OPEX there. So there's actually an early mover advantage if you innovate at layer 2, below IP. If you manage to do stuff cheaper, you're better off than your competitor. Well, of course, there's this rat hole about earnings don't making it through the waste, and I'm just showing this because network neutrality is exactly where this goes through, and I like this picture of dollars not going through an hourglass waste. But I'm here to talk about that waste. What is it with IPv6 and DNSSEC and routing security, or in the future routing security, that will make it hard to deploy? Particularly with IPv6 and IPv4, you move from IPv4 to IPv6. From the individual innovator's perspective, this is a pretty bad story. The relative advantage tomorrow is incredibly small. Compatibility, I guess we all know, it's fairly non-existent. The complexity of running two stacks at the same time, I don't have to tell you that. Triability, well, that story is changing. Observability, that story is changing too. And one of the problems here is that if you introduce new technology like IPv6, you're competing with that large N, with the large N of the IPv4 deployment. It is up to you to not spoil the fun for that big internet out there, for all those users. If you introduce that new technology, you cannot do that without extracting value from the old technology. You have to make sure that there is, any reduction of that value of that other network is in fact unacceptable. Your customers will run away. And that means that there is an early deployment disadvantage for your users, for your IP clients, that they want to have the same experience as their neighbors. So it's up to you to debug that early advantage, that new innovation. You have to debug the IPv6 with fairly little knowledge and fairly little experience from others to draw on, so the costs are relatively high. And the risks of success, it's very hard to tell the bean counters, this is, these are the risks. There are many unknowns. So with these kinds of deployments, IPv6 and DNSSEC, it's very hard to be the early deployer. That is a fairly dark picture. What can we do about that? Well, there's a solution. It's the deployer 46000. You hook it up in your network, you turn the dials, and off you go. Unfortunately, that thing doesn't exist. What can you do? Oh, this went a little bit too fast. Oh, no, this is not the one I wanted to show. That is the, so let's see. What are the things that you can do in order to move that into a direction where you actually get some traction? Well, for the group, you have to think about this McAfee law. You have to make sure that you have a credible story that in the future there will be value. Now that's a vision. That's where I say there is some engineering to do. You have to identify the attractors, the pluses and the minuses. You have to share a sense of direction and vision so that everybody knows they're walking to the same direction. That reduces the risks of going into that direction. And you actually have to reduce the cost of introducing this. Individuals, you have to reduce complexity, increase relative advantage, maintain compatibility, enable triability, and make observable that new technology for any person that is sort of, trying to do that. What are the tools by which you can do that? Well, for a group, having a credibly large future, identify those attractors and share that sense of direction, there are all kinds of tools. There's regulation. If the regulator says, and I'm not saying regulation is the best tool out there, but it is a possible thing to do. If the regulator says this is the way we want to do, they can apply taxation or subsidies in order to create that move. With taxation and subsidy, you can reduce the cost or impose a higher cost if you don't do that. You can create market. Reducing the cost and sharing the vision is also part of standardization activities, and I think we went through that. The availability in products. Wide availability in products reduces the cost and also, is a shared vision. Creating open source is one of the ways that pushes this kind of technology because it's the ultimate, sort of free things from the shelf that you can pull and run and integrate. On the other side, for an individual, having the availability of good tools will reduce complexity. The free software reduces the cost. Again, subsidy might help here. Make observable. And things like the IPv6 Day fit right into this picture. They enable the triability and making things observable. And they also share that vision of this is where we're going. But this is an easy story to tell to you. Because you all know that your network will become more expensive if you stick with IPv6 and you have to introduce carrier-grade nets. And you probably also know that if you do that, in the end, that will stifle innovation and the future internet will not be the internet in which you can do permissionless innovation and invent new protocols. You all know this, but my mother doesn't know, nor does my regulator. So preaching to the choir is easy and spreading that knowledge and spreading that vision is easy if you share the social values. You need to break out of that network to be effective. And this is where I have questions, and I really have no answers. You can adapt your message to the social values on the edge of your social network. You can speak of the managers, of the regulators, of the people of the market. Or I should say, you could try and adapt your acquaintances to support your values and principles. I think that's an important message too. Because that comes back to why we do this in the first place. This comes back to a future with 6 billion users, each with 10 devices or 100 devices. And we want to interconnect them on a global, open, innovation, trustworthy internet network. I think migrating to a technology like IPv6 specifically is needed to keep that impossible possible. Because that's what the internet is. It's the impossible thing. Same goes for security at the waist. The story there is even more difficult. because there is no compelling argument that there is an end of IPv4 addresses. The compelling argument at the moment is there ain't any more, you have to move. For security mechanisms, that compelling argument is much more difficult. The direct observables are not there. The relative advantage is not there. And I do not have good stories. So this is what I wanted to share, and hope you will take this home, think about it a bit, and maybe come up with a good story, a good solution. And maybe help with spreading the message across your social networks. And with that, I give Philip 2 minutes back.
Sorry, the microphone says it's on, but it's not doing anything. So any questions for Olaf? He ran away too quickly. No questions. I don't know how people could ask anyway. So we don't have microphones on the floor. Okay, if not, thank you very much, Olaf. Next up, we have Dave Meyer, who's going to talk about networking, the past, the present, and the future, and how software-defined networking is going to help us, or otherwise. Can we have the next set of slides, please?
All right. First off, oh wow, that timer is intimidating. This is going to be a little bit different than Olaf's talk. Basically, what this is about is sort of work I've been doing over the last 15 years in the complexity system sciences field, combined with some new interesting work that has gone on in, of all places, quantitative risk engineering and biology, systems biology. And then it all came together for me when I was studying software-defined networking. As many of you know, I've been working in the SDN OpenFlow space for a while. And so I wanted to talk a little bit about how all these things fit together and what I think about the future of OpenFlow and a more general notion of what software-defined networking is and what it might mean to you as network operators. Let's see, okay. Where's the, oops, I guess maybe this is it. Okay, so this talk will never go down in 24 minutes. And it took me almost 15 years to start to put this together. So I don't think I'll be able to get through it in 25 minutes. So I left all the slides in here, but I'm gonna skip a bunch of them. So what I wanted to talk about is what is the SDN problem space and what is the hypothesis behind it all? Some stuff about the macro trends that are inducing this new landscape, a bit about the past, present, and future, and if we get Q&A. So I'm gonna skip over some of these slides, but they're there for your reference or for your, whatever you might want to do with them. And I'll be available for questions or comments either here or email, whatever you want. So first off, wow, this talk is really going to be inflammatory to some people. It's intended to be controversial and provocative, and it's a bit sciencey, so bear with me on that, and I'll try to go easy on that. I heard that, by the way, for every equation you put in your talk, you lose 20% of your audience, so I try to keep it down. So I'm not going to do this here, but when I was building this talk, this is what I wanted to tell you guys about. And this is sort of a little bit different than what Olaf was saying, but basically, if you look at what this SDN software engineering stuff is doing, it's really creating uncertainty, volatility, and randomness above the network layer, above the thin waist that Olaf was talking about. And that's a good thing for us, by the way. But basically all this stuff is you can kind of see how it's almost inevitable. And one of the things that you might want to do is, well, how can you take advantage of it? And I don't know if you guys remember Sean Duran, but he was one of the internet guys when I started. And so I've been kicking this around with him, and I had how to take advantage of it. And he sent this little sed script that said, well, maybe you should just say survive it. But anyway, so what was the problem space? basically, early on in the OpenFlow SDN, so I'm going to call it OpenFlow SDN because SDN is actually a much larger topic than just OpenFlow, but I'll call it OpenFlow SDN. So early on in the Stanford days when this stuff was all being developed, the idea was that there's a problem that network operators are facing, and that's simply that they need to provide state-of-the-art network infrastructure and services while minimizing the total cost of ownership of this stuff. And that's a problem everybody faces. So the SDN hypothesis, what was underneath all of this stuff, was the idea that it's really the lack of ability to innovate in the network layer, in the hourglass of this thing, and in the control planes, coupled with lack of abstractions and all this other kind of software engineering machinery that was causing this. And I want everybody to think about that and kind of wonder, is that really true? And so hold on to that question. We'll come back to that. And I'll just note here that the future is inherently uncertain here. I don't know if you've ever heard this, but people say, don't skate to where the puck is, skate to where it's going to be. But you really can't do that if you don't know the curve, so you can abstractolate against it. So we'll see that that it's really not knowable. You really can't do that, and this is a consequence of this whole software world, coupled with a bunch of stuff about Moore's law and open loop control. So there's a bunch of really interesting research that suggests that this kind of uncertainty is inevitable. And so anyway, that's what's kind of interesting. So given the hypothesis, what was the problem? So, I always, when I have a slide and I don't have a picture for it, I just type the heading of it into Google Images and see what comes out. And so I got this. And, this is kind of the problem, right? I mean, you have a complicated network where all of the devices are seen as boxes. They have data planes, but there's nothing unifying them. And you have a box view, not a network view. And you also have this kind of mixture of configuration and policy. Like, the policy of the network's actually the configuration. Like Randy used to say, don't have the network be the database of record. And that's what we find. Or maybe it's this, and a lot of this stuff is maybe, protocol soup, basically, right? And maybe a lot of this is our fault, IETFers' fault, because we like to build this stuff. But what we know about this is that the network is fragile, and you know what, I can define fragility for you in an interesting way, but I'll just do it in words instead of in math for you. So basically, this is the idea. In these dynamic systems, what you have is this robustness complexity curve, and it's heavy-tailed. And there's a lot of nice research on this, but basically over here is where you're robust. And there's interesting things to notice, like the curve is concave there. And if you look at it's convex there. And if you look at where it's fragile, it's concave. And that holds up throughout all of this. But basically, if you go to the right and complexity gets greater, it's because you have increasing policies, configuration, protocol, interactions, all of the stuff you might expect. Oops. I think I'm going to skip this because this is getting, we'll look at this later if we have time. But this was the math stuff I'm going to skip. Okay, so I want to get back to these macro trends. Oh, I got this. I typed macro trends into Google and I got this out of this when I was in Hawaii. So I like this picture. So here's one of the macro trends. Intelligence evolves. And, if you look at nature, you had reptilian brain, Precambrian brain, and then you got neocortex. So you got a better processor, but what could the processor do? It could run software. And that's what we're kind of seeing happening right now. And there's a bunch of themes that are associated with this. Thin wastes, really massively distributed, highly layered with robust control loops. And and there's component reuse. And this stuff all sounds like internet stuff. So it's really all about code these days. And I'll forget about this because I didn't talk about tail events. But that's a very interesting part of all of this. So this is like a really major trend that's going on. And when I was at Cisco, I showed this to some senior execs, and when I came to Brocade, I showed the same kind of picture. And they all freaked out, oh, we're hardware vendors, all this stuff, you're killing us, why are you telling us this? And I kind of pointed out that, even in a human, with all this great processing power and software that we're running, We still have a reptilian brain to keep our hearts going and our autonomic systems going. And the analogy I like to use about this is, you know, ultimately somebody's going to have to forward packets. That's what this is like. So Olaf talked a little bit about the hourglass. So and I was saying that there's some interesting stuff happening in biological systems science and theory right now. There's this idea of bow ties. This is what they called it, the biologists. And there's a really nice paper by a fellow called Kirchner where he gets this idea of constraints that deconstrain. And this is the picture they draw. And so basically the middle part of it is what they call the knot. And in the knot you have things that are rigid, that don't change. They're the substrate for all the innovation. So you have all this stuff coming in on the left. It'll be molecules, components of other molecules and stuff like that. And then you have this reformatting of all of this. In this case, it's like into ATP, which is every cell on Earth burns ATP for energy. And then on the other side of it, you get all of life. So that's kind of what the biological systems guys saw. But wait a second. I mean, if you turn this on the side, well, you actually kind of notice that it's the same thing. And so somehow the IP architecture is kind of brilliant, and it's just like nature. So these are fundamental architectural features of the network. And one of the things you might learn from this, and Olaf pointed this out, is this is exactly the reason why IPv6 or DNSSEC are difficult to deploy. You really don't want to mess with the waist of the hourglass or the knot of the bow tie, because that's what allows all the innovation above and below. Now for us, right now, it used to be that, you know, we had all kinds of new kinds of L2 and L1 and all this kind of stuff, and we still do. We're going to have silicon optics and all that kind of stuff. But that evolves much slower because it's mostly hardware. But above, there's no reason, there's no constraint on how fast things above can evolve because of software. And that's what we're seeing right now. So it's really kind of beautiful to notice this. Oh, and then we can notice about nature is that apparently there's a paradox here. How do we resolve it? The components of the network apparently have massive uncertainty, but somehow the performance of the system is robust, right? And that's what the control planes that we have do. That's how the internet was designed. So there's a lot of things you can think about here, but I don't think we'll really have time. So I'm going to leave that, and anybody who wants to talk about any of this stuff with me, I'd love to. I had a nice discussion with Allison and Bill this morning about this. So here's another macro trend, which the vendors, at least the vendors I've worked for, really don't like, which is kind of de-siloing, right? So people like to have integrated solutions, but actually in nature, things are de-siloed. There's vertical to horizontal integration. And in our world, what we're seeing is open everything. Open APIs, open protocols, open source. Everything's pluggable. So basically, it's ecosystem. Everything's ecosystems. The future is really about ecosystems. Here's another one. This one's kind of hard to grasp, but basically, our view of the network used to be really network-centric, but it's becoming IT-centric. And I think it was Vijay who gave a talk at NANOG, I don't know, a few NANOGs ago, and what he said was, I'm not hiring any more, I don't know what he called them, but basically people who pound on CLIs. He goes, I need people who can write code. And that's what's going on here. So basically this big transition from NetOps to DevOps, and it hurts the vendors and other people because it's shifting in influence and speed and purchasing power and cost structures and all of these things. And there's a lot of standards activity around this, like over in Etsy, 20 of the largest tier 1 carriers got together and formed this thing called network function virtualization. And basically the idea here is, why can't we get the scale that IT has in networking? And that's what they're after. And it's going to happen. I think I broke this. Okay. So other important macro trends, well, everything's virtualizing, right? I mean, we're seeing that. That's not a shock to anybody. Data center, new center of the universe. Last studies I've read, 40+% of all traffic is being sourced or sunk in a data center. Dominant service delivery point, that I think everybody knows that. Integrated orchestration is almost everything. So the bottom line is increasing influence of software everywhere. And it's integrated with what I always call CSN, compute storage, identities, networking, all of that stuff. It's all integrated. And because it's software, you can do so much more. And what I wanted to, the point I kind of wanted to make is that the future's uncertain, but I didn't talk about it, but basically all this compute storage and networking power is actually increasing uncertainty and volatility, and and there's good reasons why. So, okay, so what was the past? How did we get here? So if you go back to the Stanford guys when they started to do this OpenFlow stuff, the argument was everything in networking was vertically integrated, no standards, tightly coupled, all of this stuff. Now it kind of goes without saying, or maybe it doesn't, but they certainly proposed that it did, that this made the job of the network researcher impossible. So how would you build a new control plane, for example? So the question you want to really ask, and that's probably true, by the way, but the question you really want to ask is, okay, that's true, that's cool, but what's the relationship between that, network research, and actually running or fielding a production network? What is really the relationship between that? You know, obviously things may come from research, but if you look at how innovation's worked in the internet, it's been pretty bottom up. So just to get the whole picture here, Martin Casado was a student of Nick McEwen at Stanford. When they were building this, their first thing was called SANE. It was a security architecture. And they had SANE, and then they had Ethane, which was Ethernet SANE, and then they had InSANE, which was Internet SANE. But the idea here was, essentially, it was a security architecture, and if you think about it, it was just about programming ACLs in the right place under programmatic control. And if you think about OpenFlow, what does it really do? It kind of programs classifiers, which are kind of like ACLs, right? So the salient features here were open interfaces to the forwarding plane, OpenFlow, and separation of control and data, and kind of centralized control too, right? So that was Ethane. So I just put that in there in case you guys want to look it up, read the paper. So a little later on, a bunch of people hung out in Gates 104 on the Stanford campus. That's a computer science building, and there's a big conference room, 104. And a bunch of people went there and kind of thought about this, and they came up with OpenFlow. And this was the switch model. Now, the OpenFlow switch basically had a flow table, and I'll show you a little bit more about what that is. But it had a controller, and then it had a secure channel, and that was it. And that was really appealing, right? Simple, can understand what it is. But notice, take a look at the architecture. It's separating control and data. It has a centralized control and has an open interface to the forwarding plane. Sounds good. And this is a little more detail on the switch, the same thing. Now, let me back up here. The idea here was that, again, you got to remember, the idea here was the problem we can't innovate and the problem we're having these TCO issues and all of this stuff is because networking was vertically integrated and closed. And the analogy that was being made was, we got to do what was done in compute, right? So in compute, you used to buy a VAX, it had VMS, and DEC provided most of the applications. Now we have Linux, you run an operating system. x86 is like OpenFlow. That was the analogy. But if you look at this, I got this from James Hamilton, who's a cloud architect at Amazon. Basically, it's not, the analogy really doesn't hold, because to make the analogy work, you'd actually have to have an open interface on the actual router platform and a development environment there, which is what you had on the x86 world, right? So here's a little bit of detail on that. You can kind of look at it. So this is the famous Nick McEwen thing, and here's the idea. You have a controller, you have a bunch of switches that are brainless, more or less, except for that they can talk the OpenFlow protocol, and somehow they have a control channel. And then basically the controller has applications that sit on top of it that tell the controller how to program these flow tables in the switches. And those applications would be things like OSPF. Oh, so notice the controller. It looks like it's a centralized control point, right? And that's what it was. But then people went, oh, well, you know, we've been around the internet for a while. We know that to have scale and resilience, you need a distributed system. So a little bit later on, like last year, when I was at Hot SDN in Helsinki, there's a nice paper there saying, well, if you really want to have logically centralized control, it has to be a distributed system. All of a sudden, what you have is all these trade-offs between the control plane convergence and state consistency models. And you know, in the internet, we have this really nice thing called eventual consistency, which lets us do a lot of stuff. But when you start looking at this, you basically have all the distributed systems problems. So it's no easier. It's actually harder. These aren't new ideas either. I mean, you know, we all know about SS7, Epsilon. How many people remember Epsilon, ATM, all of that stuff? Same stuff, flow switching. AT&T has this unfortunately named system called SDN. It's really for provisioning their Sonnet SDH infrastructure. A lot of times people say, oh, this is the same as the TDM voice, packet voice thing, right? Where the soft switch is like the controller, the media gateway is like the switch, and H248 is sort of like OpenFlow. I don't know. I mean, I'm a little less convinced by that. And then there's forces in the IETF, and it goes on. So people have been trying to do this because centralized control is really appealing. It's easier. So here's the switch, right? This is what it was. A packet would come to it. It would hit the flow table, which was a TCAM, basically what it could do is, if there was a rule, if there was a match, it would apply the actions and forward the packet, or you could configure it to drop the packet or send it to the controller, in which case the controller would set up the flows along the path, basically a soft PVC. So what's the problem here? Well, it's conceptually simple and attractive, but it's too simple. So there wasn't feature functionality. It couldn't do L3, for example. There was no way to decrement a L3 TTL in OpenFlow version 1, so you couldn't do anything with IP with it. And the actual language that you used to program it was lacking. It wasn't expressive enough to do some of the things you wanted to do. So what happened? This is the current state of the world. This is the current OpenFlow switch model in the current spec. So basically, it's a bunch of these undifferentiated tables hooked together. N of them, whatever N means. If it's software, N can mean 256 because there's 8 bits. If it's hardware, you don't know because hardware is hardware and it has whatever it has. Now, what's the deal with this? Well, the design was to get around the combinatorics of the rule cross-route explosion that you have in one table. But if you look at this thing, the complexity of this is pretty nasty, right? It's n factorial because there's n ways to choose the first table, n minus 1 ways to choose the second, blah, blah, like that, right? But it's worse because there's some number of actions per rule, and then there's some width of bits that you can match on from 0 to the width of the match fields. So it's pretty difficult to actually consider how many paths there are through this thing. And so it's too complex. There are questions like, what is a flow now? You don't really know. And by the way, it gets instantiated at runtime, so there's no way a priori to know. It's not naturally implementable in ASIC hardware, and I can explain that. There's a lot of reasons for that. It breaks all these really interesting new reasoning systems like frenetic that Jen Rexford and her colleagues and Nate Foster at Cornell did. There's no fixes for lossy abstractions, and I didn't have time to talk about what that is, but if anybody wants to know, I'll let you know. And there's other architectural questions that have to do with the breaking of the fate sharing between the control and data plane. And in the meantime, there's other versions of SDN that are coming along that aren't OpenFlow SDN. So, and you see these being standardized in the IETF and ETSI and ATIS everywhere. You know. So the question I think we ought to be asking here is this flow-based abstraction, is that really the right thing, right, for some value of right? I have like 3 minutes left. For general network programming, and my answer is probably not. So I kind of cooked this up. So look along the bottom. On the left side, you have this really, which is sort of a radical design point. This is OpenFlow SDN, right? You have open interface to the control plane, complete separation of control and data, and then if you move to the right a little bit, there's something that I'm calling control plane SDN. This is where you have programmability of the control plane. So I2RS in the IETF, PCE, even netconf could fit in this category. And then if you go all the way to the right, you have what is sort of Nicira VMware. It's like you give me 3264, 128 ECMP by 10 ECMP or something like that, and I don't care what the controller data plane underneath there is doing, I'll put my own on top of that. There's all kinds of reasons why that might be suspect too. So where's it all going? Oh, okay, so I put the future into images and I got that. And I don't think it's supposed to mean we're drowning in garbage, but, you know, anyway. So more seriously. Sort of the way I'm looking at this is that the software that we're building is uncertain. So we're gonna need to architect above the waist for change. And we're gonna have to start learning about what that change means to us. And so a good example of what can happen above the waist is spot cloud. Anybody looked at spot cloud? It's basically a spot market for VMs. Spot market is the most volatile thing there is. So, and not only that, what these guys did was they built what's called an OpenStack connector for the buyers and the sellers, and the sellers can be anywhere in the world. So now all of a sudden you have a cloud, and on top of that there's another cloud with the VMs all scattered all over the world, and you cannot know very much about the traffic patterns or anything with that. So it's kind of a higher order bit is uncertainty. You know, we're going to see all this conventional technology curves. That's the reptilian brain stuff. Speeds and feeds, Moore's law, silicon optics, denser cores, all that stuff's coming. And by the way, all that adds to uncertainty too. Oops. I don't know what happened there. Okay. As I mentioned, the future's about ecosystems. I think this really, really going to happen. People say to me a lot of times, well, you know, what about, who do I point the finger at if this thing's all an ecosystem? Well, you know, when you have a router, the router has Broadcom chips in it, it's got memory from somewhere else, it's got software from somewhere else, it's got CPUs from somewhere else, and the actual router vendor is a system integrator. So this is just another kind of system integration, and it's going to happen. Open source. Now, so this is a question for this kind of group. It's like if open source and open source consortia are dominating, oh, I'm out of time. You know, we have to think about how that interacts with our standards world. Oh, okay, so I'm done. I'm out of time. So I don't have enough time to, am I really done? Totally? Let me show you one more picture and then I'll go. So this is the kind of thing that's happening, is that basically there's this middleware that people are building, and it's got these attributes that on the south end of it, it talks all these different protocols, and the architecture is plug-in, right? So if I want I2RS, if I want OpenFlow, if I want PCE, NetConf or anything, I'll build a plug-in and I'll talk to whatever gear I want to talk to. Northbound, the same thing. So what this thing is sort of like a state management layer. And so these things are starting to pop up everywhere, and they're also layered, recursively layered. So I think we're going to see a lot of this, and this is, again, going to add to the uncertainty. But fortunately for us, we're working in the narrow waist part of in the part of this whole architecture, and so we're in the most stable part of it. And I think I'll just give up here. But if people have any questions about this, please contact me or send me an email or pull me over. There's a lot more to talk about here, but that's how I'm kind of seeing it. Out of time.
So thanks very much, Dave.
Okay.
Any questions?
Feel free to pull me over if you like.
Okay, thanks very much. So final speaker we have is Kobi Hasharoni from Compass EOS, who's going to talk about chip-to-chip optical interconnects on routers and things. So can we have the slides up?
Okay, good afternoon. First I have a disclaimer. I'm not from the internet world, so I'm not going to talk about IPv6 or anything like that. I will talk about how optics should penetrate into core routers. So the outline of my talk, I'll discuss the problem of core routers and how photonics are a viable solution, and then what we do in Compass. So I guess you've seen these graphs many times. Basically, I think it's from a study by Cisco. It shows the growth of internet IP bandwidth with an extrapolation for about 5 years ahead. And as you all know, the demand for bandwidth increases continuously at a huge rate. And yet the infrastructure is already maxed in terms of size and especially bandwidth. And of course, routers are huge, they are power hungry, they are big and heavy. And there's no roadmap looking ahead. How can we deal with the ongoing demand for IP traffic? So what we need is some drastic change in bandwidth, size, and capacity. However, if you wanted to go to high bandwidth systems, there's a price to pay, mostly power. So this is a calculation done by a Belgium group about power consumption of ICT services. And you see that in the coming year, the amount of power consumed by ICT services is huge, 350 terawatts per year. This amounts to about 2% of the total electricity produced in the Western world. This is unacceptable at any rate. However, on the other hand, ICT services are growing at an annual rate of about 40%, probably more. So we are in a kind of a problem. And as you probably well know, better than I do, core routers are responsible for most of the power consumption in ICT services. So this is a huge problem. How do we cope with this energy demand? Then there's another price to pay, size and weight. As you probably know, core routers are big, heavy, they require special building, concrete floors, etc., and mostly they require a special electricity, high power line. Another way of how routers are designed, let's assume that we have 4 line cards in a typical router. It could be more. We have actually 3 types of chip-to-chip interconnect. We could have chip-to-chip within the same board. I mean, we have to move data between chips on the same board. We could have board-to-board interconnection via the switch fabric. So between 2 line cards or several, we have to shuffle data back and forth between various line cards. And lastly, we can have it between racks, like in a multi-chassis situation. And the bottom line is that conveying the data between the line card is the biggest problem. That's the bottleneck of routers. Why is that such a big problem? Let's look at a typical case. We have two CMOS chips doing whatever forwarding tasks we need. The problem is that we need to move data from one CMOS chip, the one on the left side, to the one on the right side. So how is this done? we're doing it on high-frequency serial links on the PCB. These are basically copper traces on an organic board. When you go to high frequency, you come up with a big problem, because the higher the frequency, you meet several problems. Most prominent are skin effect, dielectric loss, impedance mismatch, crosstalk, and there are a couple of other problems. In plain English, the higher the data frequency is, the higher the loss is. So at 10 or 10 gigabit per second, you can't actually drive data for more than 3 or 4 inches on the board. And if you have to go across a board which is this big, like in any common router, you have to plug in buffers and equalizer in order to reconstruct the signal, because signal integrity is the basic feature that we must maintain. This means that you have to add more and more electronics in order to reconstruct the signal. And therefore, your power consumption goes up, and the router becomes bigger than I am. And this is why common routers are so big. And that's why they're so power hungry. So it's not the processing itself, it's moving data between the ASICs, which is the problem. And this problem is only going to become more severe. There's another problem, except for this connectivity issue. How do you push all this bandwidth into a single CMOS chip? So now you have this forwarding engine of switch fabric, and you need to shuffle in tens of gigabit of data. But BGA technology is limited. Today, the pitch of BGA technology is 0.8 millimeter. It might go down to 0.6, who knows, maybe 0.5, but basically, you are running out of scale. So what can you do? Well, first option, you can split the data into several CMOS chips, meaning more power, more sides, etc., etc. You have another option, push the limit of electrical SerDCs on the board to higher frequencies, like 25 or 40 gigabit. Then you'll have to go to 20 nanometer technology, perhaps more, if there will be another technology. But then, we just said that you can't really keep pushing data faster and faster, because there's a limit of how fast you can push data or how much bandwidth you can push on a board without getting into all those signal integrity issues. So these two problems, the chip density problem and the chip interconnect issues, are really the biggest showstopper for core router design. So in the next few slides, I'll discuss the natural solution, which is to go to photonics. As you probably know, Moore's law has been, for the last few years, has been declared to be dying, because silicon technology cannot shrink forever. And there is a well-known convention that must move on to photonics. We believe that the time is now, and I'll show you how. So first of all, why should we go to photonic solutions? First of all, photons are insensitive to the data rate. So they can work at 10 gigabit, they can go up to 100 gigabit, you don't really care. There's no significant problems. Then the power consumption is relatively small, much lower than copper traces on PCB. Crosstalk is practically non-existent. And you can drive it, at least with multimode fiber optics, for 200 or 300 meters. This is something that there's no way on earth you can do it with copper wires. You cannot drive high frequency over copper. Now, if you're using parallel optics, meaning a lot of fiber optics together, your efficiency is very high. And the added benefit is that the footprint of this optical interconnect on your silicon processor is very small, and therefore you don't have to waste all of your silicon real estate on chip I/O. You can actually focus on doing the logical stuff on the silicon and having the data coming in and out via an optical solution. So coming back to the previous slide, again, we have traffic coming in, being processed, and being shuffled via high-frequency serial links on the PCB. But this, again, is a big problem, so we must get rid of it. And now we have to replace it with an optical interconnect between the routing elements. So we're going to have forwarding engines, router elements, and they should be connected via optical links. So first of all, what's this optical interconnect? So I also looked in Google for some images. So in a very simplified manner, basically we have a laser transmitter, a laser diode. This is a simple one, of course. We have a photo detector. Each one of them has its own analog electronics, laser driver in the laser case, and trans impedance amplifier and limiter amplifier in the receiver case. Now we link them together using fiber optics, and this is basically an optical interconnect or an optical transceiver. So how would you do an optical interconnect-based router? How would you do that? So you've got a few problems, and you have to solve them. First of all, you need to establish an optical connection between the line cards. Well, that's easy. Like I just said, we put a transceiver, an optical transceiver on each CMOS chip. On each chip, which has to push in and out a lot of data, you put an optical transceiver, which will basically shuffle the data back and forth. The next problem is that the connection must be data rate independent. Otherwise, we haven't done anything. Well, photons are data rate insensitive. There's no crosstalk involved. Now, the problem, as we stated, is that your bandwidth is increasing, so you need to move huge amount of data between the line cards. So the solution is use parallel optics, meaning don't use a single laser diode like I showed you on the previous slide. Use a matrix, a two-dimensional matrix of lasers and detectors, and put as many as you want. That way, your efficiency will be very high. Minimal power consumption, of course, is another key issue. And if you do the analog design, mostly the SerDes is designed carefully, and you use lasers which consume little power. Mostly they're called the VCSELs, vertically emitting lasers. You can do it. Last but not least, the backplane should be passive. The whole idea here is to get rid of the switch fabric. So if you want to get rid of the switch fabric, which is basically copper-based, you replace it with fiber optics. If your backplane is built from fiber optics, it is 100% passive, it doesn't consume any energy, it doesn't degrade the signal, and you're ready to go. So your optical interconnect, schematically, would look like that. You have your CMOS chip doing whatever digital task you want to do, and you have a matrix of transmitters, named lasers, and a matrix of receivers. Matrix size is as big as you want it to be, and you have fibers connecting them in between, moving the data back and forth. So having established how the optical interconnect should look, I'd like to spend the next few slides showing you how at Compass we implemented that into building a core router using a photonic solution. So going back to the schematic router layout, again we have a line card, and each line card has its incoming ingress and egress buffers, and you have the forwarding engine, and you have the buffers going to and from the switch fabric. So the first task in building this photonic-based router is to get rid of all the bottlenecks involved. First bottleneck is the egress forwarding engine. You really don't need it. So let's get rid of it and put some egress, forwarding egress tasks into the output, the egress buffer. Then the next step is, let's get rid of the switch fabric completely. Throw it away. And you are left with two line cards. You need to connect them somehow. Well, we put an optical transceiver on each of the chips, and we have an optical link between them. Of course, the key point is that the data link must be fast enough. In order to be much faster, you must have a speed up compared to the incoming in traffic. That way, you will not feel the congestion. So you have your optical link between the processors, and now the switch fabric tasks are actually grouped into what used to be the egress queuing buffer. So now, actually it's a new chip. This is the chip designed by Compass, EOS, and it's a data plane chip, the device. Basically, it gets the data from the forwarding engine and pushes it via an optical link to whatever chip client requires it. And of course, you can implement it with full mesh configuration, meaning that all of your data path chips in the router can talk with each one, and if you have a full mesh with all its benefits. So basically, the way you do it, you have a chip-to-chip optical interconnect. It's a true output buffer switch router, You don't have the switch fabric, no ingress side queuing, but on the other hand, all of the functionality of core routers is actually maintained. The big problem is, how do you do it? Up to now, it was all very nice by showing PowerPoint slides, but you really have to implement that. So the first step into building such a router would be to get the optoelectronic chips, or in other words, the lasers and receivers. We are using VCSELs. VCSELs are much more efficient than side-emitting lasers, which are more common to the telecom industry, because you can group them in matrices, two-dimensional matrices. What we see here is an actual image of a VCSEL. I don't have a laser pointer, but each one of those, actually what we have here is a 12 by 14 matrix of lasers. I guess you can discriminate them. Each one has about 6 pads around it. So we have 168 lasers. Similarly, you'd have a matrix of 12 by 14 matrix of photodiode. Then again, this 12 by 14, the 168 elements, derives from whatever architecture you want. You can have it 10 by 10, 16 by 16. It's really up to you what is the optoelectronic matrix chip. And then you have the same 12 by 14 matrix of microlenses, etc., etc. Everything you do is two-dimensional chip sized. This is an example of a 12 by 14 VCSEL matrix. We see the eye diagram from each one of the VCSELs. They look all the same, but trust me, they are not the same. So this is, to the best of my knowledge, the biggest VCSEL matrix operating in the world. And actually, you can also, sorry. If you look at the eye diagrams, those who are skilled with this art can actually get an impression of how nicely open the eye diagram is. It's not a trivial task because these lasers are adjacent to each other and they have to be really electrically isolated. So what's the next task? Now you have to design a CMOS chip, this data path chip, which will handle queuing, the egress processing, the egress buffer, the switch fabric, and of course the optical transceiver. This is how it looks in reality. We do it in a TSMC CMOS process, and you can see in the center of the chip, you can actually see an area which is for the analog circuits. So basically, you have a hybrid chip, which is digital and analog together, with the analog electronics in the center of the chip. And if you can, you can see the analog part consumes only 10%, more or less, of the total silicon area. This means that 90% of your silicon real estate, which is the most expensive part here, is free for your digital tasks. Therefore, this data or router chip is very, very efficient. The third step is the biggest problem. How do you assemble optics on chip? Why is it a problem? Because lasers and photodiodes are not made from silicon. They are made from materials which we call 3,5 materials, like gallium arsenide, indium phosphide. Silicon, on the other hand, is silicon. Those two materials don't really like each other because they have different coefficients of thermal expansion coefficients. So it's not so easy, but it took us a few years. But basically, it's possible to put these large matrices, and these are very large matrices. These are 3.5 by 4 millimeter VCSEL and photodiode matrices. You can put them on the silicon, having a direct electrical link. So what we see in this image is the silicon chip with a matrix of lasers and a matrix of detectors directly assembled on it. So again, this is one of the few examples of optoelectronic chips assembled directly on a CMOS chip. So here's the VCSEL matrix, again lasers, and here's the photodiode matrix. And now the next step is you have to package it. So you take an organic package, which is common in the industry, and you see on these two images, you see the chip on one side, and on the right side, you see the BGA part, which actually hooks to a PCB. Notice that there's a hole in the center for the optics, for access to the optics. The fourth step will be you need fiber optics in order to get the data in and out. So basically, in simple words, you take 168 fibers, you put them in a silicon head, and you build a 12 by 14 fiber matrix. This is how it looks in reality. Actually, we have some of the fibers are illuminated, so you can see light coming through. and you have a fiber bundle. Fifth step is assemble everything on the PCB. So now you take your CMOS chip, you assemble it on a PCB, and on the other side, via this hole that I showed you, you couple the fiber optics, those fiber bundles, just above the lasers, you glue it, and you have, basically you have a router at hand. Actually, this is not only part of the router, so you integrate it with the line card, and you build a high-end core router. So this is the line card. Basically, you can have, in this case, we have two optical engines. You see them with the black heat sinks. And eventually, you have a high-grade, high-end core router. And notice the size. It's of 6 rack units, meaning it's about this high. Compared to a Cisco or Juniper router, this is about 80% smaller. And it's all due to this optical interconnect technology. So just to summarize, the optical interconnect enables you to build a new class of core routers and edge routers. Actually, this technology is not only limited to telecom routers, it's very useful in the data center, and of course, it can be used in high-performance computing, optical memories, etc., etc. Whenever there's a task which requires you to go into the silicon chip, get the data out, move it to another silicon chip, and stick it inside, this optical interconnect technology allows you to do that. What do you gain? Low power consumption, smaller size. If you've seen, we dropped from 47 rack units to about 6 rack units. That's a huge drop in size. The weight from about almost a ton, it's less than 100 kilos. So basically, you can pick it up yourself, or two guys can pick the router and put it in the 19-inch rack without a forklift or without anything, actually. The bandwidth, of course, is very high because, again, most of your silicon power is utilized for digital tasks and not for chip I/O. And again, most of the chips that high-capacity chips are, most of the time, are busy doing I/O. Last but not least, it's a lower cost because it's a much more efficient design. So some numbers. This is this optical interconnect is the highest reported interconnect in the world. It has an aggregate bandwidth of 1.3 terabit per second. There's not even a single optical system. Of course, there isn't an electronic system which even comes close. The data density is 64 gigabit per square millimeter. Again, this is the world record. We use, in this case, 168 bidirectional 8 gigabit lines. Most important, power efficiency is 10 picojoule per bit, including the SerDes. Usually when people show you the power consumption, they tend to forget that there's a SerDes behind, and they show you only the laser driver and the transimpedance amplifier. That's very easy. You have to take into consideration these optical SerDes, which are power hungry. So 10 picojoule per bit is a very impressive number. So this is the Compass core router. Actually, it's been shipping, so it's 1.6 terabit system, 6 rack units, 4 line cards, each one is 200 gigabit, 3 kilowatts, front to back airflow, blah, 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 carrier grade, full layer 3 functionality, multi-chassis support, of course. Regarding multi-chassis, I should say this is a switchless system. So in reality, you can hook up together 21 of these routers to get a huge multi-chassis system without a switch, because it is a switchless device. It is NEBS and ETSA compliant. This is the backplane. I have 43 seconds. Completely passive optical backplane. Oops. Okay. And there's a path to 2 terabit line card. We can either scale up, meaning going to 32 gigabit, for example, or we can scale out, doubling the matrix size. If you combine those two things, you can end up with an optical interconnect of almost 11 terabit per second. And this will be achieved within the next 2 years. 11 terabit per second, this will allow you to have 2 terabit per line card. Because again, you need a speed up of the optics in order to push the data from the input. Last, if you look at the total cost of ownership, comparing some common Cisco, Juniper, and ALU machines over a 5-year period, taking into consideration cost of ownership, power, cooling, space, etc., you can see that this optical interconnect system is significantly cheaper over a 5-year period. And again, this is all due to this this optical interconnect technology, which allows you to considerably reduce price, power, cost, and size. So thank you for your attention.
Thanks very much, Kobi. Does anybody have any questions? Doesn't look like it. Well, you have plenty of opportunity in the coming days to discuss the presentations with our 3 speakers that we had in the first APOPS session. So I would like to thank Olaf Kolkman, Dave Meyer, Kobi Hasharoni for their presentations. We hope they've been interesting for all of you. So we ran over a little bit. Apologies for that. I was a bit slack in getting us started early on this afternoon. So those of you who got social event tickets, the buses leave soon to the Jewel Box, so please make sure that you're on time for those. Those of you who are not going to the social event, I hope you enjoy your evening. Just again, quick reminders to the speakers for the rest of the week. If you're still in the room, please, we need your presentations to be uploaded so we can publish on the website. This room is going to be divided in 2 tonight, so there'll be 2 parallel sessions. Again, we'll have the same arrangements, speaker, laptop, and so forth. So we need the presentations as quickly as possible, please. This also helps the participants. Many participants would like to download the slides and follow the presentations as you give them. And having the presentations on the website makes it easier for them to follow a lot of the discussion. So thank you all for that. Enjoy your evenings, enjoy the social event, and we'll see you all tomorrow morning. Don't forget about the breakfast, which is available from just before 8 a.m. in the room next door. Thank you all. See you tomorrow.